Dopplers. So again, when we talk about Doppler echocardiography, you need to understand the Doppler effect. What is the Doppler effect? You need to have a basic understanding of the Doppler shift formula, why you get certain spectral recording. We went over that. Pulse wave Doppler, what is pulse wave Doppler? What are the limitations of pulse wave Doppler? And then we're going to finish up tonight with continuous and color flow Doppler. So just briefly recapping what we did, we talk about Christian Doppler, who first described the Doppler effect, and we tried to describe what the Doppler effect is. A very common example of the Doppler effect is if you're standing still and a car is coming towards you and the horn is going, and the car is coming towards you. You will get you will have the perception that the frequency or the intensity of the sound is increasing when the car approach you. But as soon as the car move away from you, you'll perceive that the intensity or the frequency is decreasing. So that is what the Doppler effect is. It talks about a moving source of sound, a moving source of sound. So we use the example of the car when the horn is going. So if the car is moving towards you, then that's the moving source of sound. The horn is the sound. So the person is pressing on the horn and the car is moving towards you. When the car approaches you, the intensity seems to be increased or the frequency seems like it's increasing. But as soon as it moves away from you, the intensity or the frequency seems to decrease. Okay, so what I just described is a moving source of sound, and we went over that. This is the Doppler shift formula, where the Doppler shift delta F is equal to the received frequency minus the transmitted frequency, and we try to separate the frequencies. You have a transmitted frequency and a received frequency. The received frequency is actually a perceived frequency. When the car is coming towards you and the person is pressing on the horn, that transmitted frequency, because the horn in the car is going to make the sound. They're pressing and the horn is transmitting sound at a fixed frequency. Okay? At a fixed frequency. And that is what we call the transmitted frequency. However, when the car approaches you, the what you call the received frequency or the perceived frequency seems to be higher because you have a moving source of sound. When the car moves away from you, the transmitted frequency is the same because the person is pressing on the horn, same intensity, same transmitted frequency. But the received frequency, because you are the person who is going to receive the frequency. So when the car is moving away from you, that received frequency is going to be reduced. Okay? And the Doppler shift is the difference between the received frequency and the transmitted frequency. And we look at the formula. This is the Doppler shift formula. So you need to have some basic concept of the formula. So the Doppler shift, this V is the velocity of, so we're talking about ultrasound now. However, if you were talking about the same car that is moving towards you, then this would be the velocity of the car, all right? The velocity of a car which is moving either towards you or away from you. And then this C, if we're talking about the car, moving source of sound, the horn in the car, then this C would actually be the the velocity of the sound in here. But when we do Doppler uh, in the human body. You know, you can do Doppler anywhere. As a matter of fact, in aeronautic engineering, you know, things like that, they use a lot of Dopplers. In any hydraulic thing, they use a lot of Doppler. The same principle, but we use it in echocardiography because when we when we image the heart, blood is moving towards the transducer or is moving away from the transducer. The heart tissue itself is moving towards the transducer or away from the transducer. So we have a lot of things moving, and that is good because we can use the Doppler shift formula, especially in the heart, to to get velocities. And once we have velocities, we can convert those velocities into gradient, and we can use those gradient to do all sort of stuff. All right. So Doppler is the cornerstone of what we call hemodynamics. Hemodynamics is when we calculate gradients in different parts of the heart. We can calculate valve area. Um, you know, so hemodynamics incorporates Doppler, and we use the the Doppler to allow us to calculate all different things. And so a thorough understanding of Doppler is important. The important things in the formula, so this is a Doppler formula. The important thing is this angle theta, as we discussed before. That is the angle that the beam, ultrasound beam, makes with the moving structure, whether it's blood or it's the heart muscle. Okay? You want to make this angle as small as possible. Okay? And we'll look at how you do that. So the angle theta is the angle between the ultrasound beam and the transducer, that is from the transducer and the moving structure. You know, whatever moving structure you're looking at, you want to keep this angle as small as possible. And again, C, velocity of the sound in blood. Okay, if you were say looking at the, because we look at the base of the heart moving up and down, we use Doppler for that as well. So it would be the velocity of the sound in the soft tissue, the heart. So you know, you can substitute this C for the velocity of the sound in that structure. And then the V is the velocity of blood. Okay, so you need to have a basic understanding of the Doppler shift formula. We talk about if the say let's use blood for example. If the blood is moving towards the transducer, then same thing as the car moving towards an observer. Okay, you'll get the received frequency will be somewhat higher. Okay, and as opposed to when the blood is moving away from the transducer, the received frequency is going to be reduced. And we usually uh, represent frequency as, you know, the wave. You can see these wave uh, configuration. So when they bunch up like this, that means increased frequency. When they spread out like that, it means decreased frequency. Okay, so when you have your ultrasound, your transducer, or your probe, remember the sound wave that you produce is going to go straight, it's going to travel in a straight line. If the blood is moving like that, then the ultrasound beam is going to make the ultrasound beam is going to make an angle with the moving red blood cells. Okay, this is the angle that we're talking about, theta. Okay, so the ultrasound beam coming from the transducer or probe is going to come straight down. Okay, the moving red blood cell is going to move horizontally. You want to make this angle as small as possible. Okay, you want to make this angle as small as possible. If you can get the angle to be 0, that is what you're shooting for. If the angle is 0, then the ultrasound beam is going to be parallel to the moving red blood cell. And we the reason why you want to make the angle small as possible because the cosine of the angle. Okay, remember the cosine of 0 is 1, the cosine of 90 is 0. So you'll get a much larger number if this angle is very small. All right. Okay, we look at the spectral recording, how we get different spectral recording. If the flow is towards the transducer, you're going to get a display which is on top of the baseline. Call it it's going to be positive. You got an upward shift in the velocity. If the flow is away from the transducer, it's going to be below the baseline, and we show you how that this is. So these are spectral drawings. Okay, so if you have a flow, anything that moves towards the transducer is going to give you a spectral envelope above the baseline. Okay, if you have a flow, anything that moves away from the transducer going to give you a spectral envelope below the baseline. And those basic concepts is very important because you can look at, say, this spectral envelope and say exactly what's going on. You have a cursor. This is a short axis at the level of the aorta. Your tricuspid valve is over here. Your probe is always up here, and you have different symbols to represent the probe. Okay, this is your cursor, and you have, so your cursor is here. So this is what you're sampling. Your probe is right here, or transducer. This is the baseline, and you have an envelope which is below the baseline. What that is telling you, you're having a flow, which the flow is moving from this area across this structure down here. The flow is moving away from the probe. That is why it's below the baseline. Not only that, you have your ECG right there, and you know that systole is from the onset of the QRS to the end of the T wave, onset of the QRS to the end of the T wave. So you're getting this systolic flow below the baseline, okay? This short axis at the level of the aorta, the tricuspid valve is right there, the right ventricle is right there, this is your right atrium. So this flow is moving from the right ventricle across the tricuspid valve into the right atrium. So this is tricuspid regurgitation. Okay, blood moving backwards from the right ventricle across the tricuspid valve into the right atrium. And then we looked at this one. So your transducer is depicted right there. And this is your apical four-chamber view. Your cursor is right there. The sample volume is at the tip of the mitral leaflet. Okay, ECG is right there. But this time you get these envelopes above the baseline. These envelopes are above the baseline. So let's figure out what's going on. So above the baseline, it tells us that the flow is going towards the transducer. If the flow is going towards the transducer, then the blood is going to flow from the left atrium across the mitral valve into the left ventricle. The blood is flowing in this direction because the envelope is above the baseline. So this is what we call the mitral inflow. You remember, blood is going to flow from the left atrium across the mitral valve into the left ventricle, and this is going to occur in diastole. Diastole is from the end of the T wave to the QRS, the end of the T wave to the QRS, the end of the T wave to the QRS. So you see that these are diastolic flow, diastolic flow. So in diastole, we know that the mitral valve opens, blood is going to flow from the left atrium into the left ventricle. So you have diastolic flow. But there are two flows. We already we taught you this in physiology. When the mitral valve opens, you get an essential suction of blood from the left atrium into the left ventricle. You get your so-called E velocity. Then you get a cessation of flow because of equalization of pressure. So you get a diastasis, and then the atrium contract to give you A velocity. So this is your E velocity and your A velocity. Okay, this is your if you rearrange the formula, you get this is the velocity of the moving red blood cell. And if you rearrange the equation, then uh, you get this, the Doppler shift. Of course, if you try to remember, your Doppler shift is equal to 2 times transmitted velocity times V minus the cosine of theta over C. Okay, so remember what your V and your C is. Okay, it's important to distinguish them. Again, you see this angle, you want this angle, and that is why when you're doing ultrasound, you always have to use multiple windows. You have to do the scan from multiple windows, because what you're trying to get this angle as small as possible. Okay, you're trying to get the ultrasound beam parallel to flow. Okay, you're trying to get this angle as small as possible. You're trying to get it 0. Again, cosine of 90 is 0. The cosine of 0 is 1. Cosine of 90 is 0. So remember that. And that is why if your ultrasound beam is perpendicular to the flow, you're not going to get anything. You're not going to see anything. Okay, you're not going to see anything. All right. All right. So now we come to pulse wave Doppler. Okay, there are different types of Doppler, and one is the pulse wave Doppler. Now, the pulse wave Doppler is limited by the velocity that it can measure. Pulse wave Doppler can measure low velocity flow. Once you talk about a higher velocity flow, you cannot use pulse wave Doppler. Okay, so when we talk about pulse wave Doppler, it measures velocity of blood at a single point. Okay, the transducer, that same transducer that you're using, is sending out signal, and then it's waiting for the reflected signal to come back. So that same transducer is sending out and waiting for the signal to come back. Okay, so the transducer is alternating between transmission and reception. So it's sending out and receiving. We use pulse wave Doppler to measure mitral inflow that I just showed you, left ventricular flow tract velocity, hepatic vein velocity, tissue Doppler imaging, pulmonary vein, and tricuspid inflow. So those are things you have to know. Because you have to know when you're doing your study, you have to know when to use pulse wave Doppler, when to use continuous wave Doppler. Again, this is your mitral inflow, okay? And in diastole, you get your E velocity, you get a diastasis, A velocity, E velocity, diastasis A velocity. Use pulse wave Doppler for this measurement. Pulse wave Doppler is limited because it can only measure velocities, say 1.5 to 2 meters per second. It can only measure relatively low velocities, 1.5 to 2 meters per second. We use pulse wave Doppler to measure left ventricular flow tract velocity. So this is your cursor, apical four chamber view, transducer or probe is right there. You want to put your sample volume a little bit outside of the aortic valve. So you want to put it right there. Okay. The blood is now flowing from the left ventricular cavity to the left ventricular flow tract across the aortic valve into the aorta. So it's moving, the blood is moving this way, it's moving away from the transducer. That is why it's below the baseline. It's a systolic flow, so it's from the onset of the QRS to the end of the T wave. Okay, or hepatic vein velocity. So remember, the hepatic vein drains into the inferior vena cava and it's moving away from the transducer. Okay, so that is why it's below the baseline. You have a systolic component and a diastolic component. So you have to sort of visualize the liver. Okay, remember the hepatic veins are inside the liver and they are draining into the inferior vena cava. The blood is flowing away from the transducer. That is why it is below the baseline. So in systole, you have the systolic component. In diastole, you have an atrial reversal flow. Tissue Doppler. So we can look at the movement of the heart muscle, and we usually look at the movement of the mitral annular plane. The tissue or the heart muscle doesn't move as rapid as, say, the blood. So the velocity of the tissue is less than that of the blood. But it's, we get a lot of information by measuring the velocity of the heart muscle. So it's a crucial measure, and we call this tissue Doppler imaging. We put our sample volume, say, at the medial annulus or the lateral annulus, and when the heart contracts, we know that the annulus of the heart moves up towards the apex. So the base of the heart right here moves up to the apex, and we can use Doppler to look at the velocity of these movements. And when we turn our tissue Doppler velocity button on, we get something looking like this. Okay, in systole, the base of the heart moves up, and we get what you call a S prime. Remember, your ECG is there. Everything in echo is gated. So you always, if you're gonna do a study, you don't have the ECG, well, you shouldn't do the study. But anyway, so your ECG is right there, and in systole, the base of the heart moves up. Okay, the transducer is right up here, so the medial annulus and the lateral annulus moves upwards. It moves towards the transducer, so you're going to get this above the baseline. In diastole, the annulus moves downward. It moves away from the transducer. That is why you get these envelopes below the baseline. You're going to get an E prime and the A prime. Okay, these are diastolic velocities. Very important, so you have to know what they mean. So both on the medial and the lateral side, you're going to get your systolic component, which the mitral annulus moves up in systole, in diastole it moves down. Anything that moves towards the transducer is going to be above the baseline. Anything that moves away from the transducer is going to be below the baseline. Okay, again, this is pulmonary vein flow and apical four-chamber view. Your sample volumes, your cursor is right there. The sample volume is right there, and you just press your pulse wave button, and you get a systolic component, a diastolic component, and an atrial flow reversal. Okay, so remember the pulmonary veins drain into the left atrium. When the ventricle is contracting, you still get flow from the pulmonary veins into the left atrium. When the ventricle relaxes, you still get flow. However, when the atrium contracts, it's going to push the blood in the opposite direction. So you'll get, it's going to be below the baseline. Your transducer probe is right there. So when the atrium contracts, it's going to push blood away from the transducer. The blood is going to flow away from the transducer. That's why it's below the baseline. So your pulmonary vein flow, you're going to have your systolic component, your diastolic component, atrial flow reversal down the bottom. Okay. All right. So again, your pulse wave Doppler, the limitation of the pulse wave Doppler, it can only measure low velocities. It can only measure low velocities, 1.5 to 2 meters. Okay. Uh, Anything above that, you can't use your pulse wave Doppler. You get what we call aliasing. So if, say for instance, you use pulse wave Doppler to measure a velocity of 3 meters per second, when it reaches 2 meters per second, it's going to cut off and it's going to put the additional 1 meter per second below or above the baseline. So that's what we call aliasing. So aliasing is represented on the spectral tracing as a cutoff of a velocity. And this is what it looks like. So if you were, say, imaging aortic insufficiency and say the aortic insufficiency was 3 meters per second, in this first scenario, you use pulse wave Doppler. Once it gets to 2, it's going to cut off the top and put it down the bottom. But if you were to switch to something that can measure the full spectrum of the velocity, you can see it's 1, 2, 3. It puts everything where it's supposed to be. And this is when we use continuous wave Doppler. You can do that. You can measure the full velocity. Pulse wave Doppler, once it gets to 2, 1.52, it's going to cut off the top and put it at the bottom. So when you have high velocity flow, you have to switch to continuous wave Doppler. So continuous wave Doppler measures blood flow velocity along the entire line of interrogation. When we talk about continuous wave Doppler, it's continuously sending out signal and receiving signal. There is no wait for reflected signal. It's continuously sending out and receiving. The transducer continuously send out pulses of ultrasound and continuously listen for the reflected frequency shifts coming back. Okay? It's sending and receiving at all time. So if you have high velocity to measure, you use your continuous wave Doppler. So we use continuous wave Doppler to measure high velocity flow. So some of the high velocity flow, mitral regurgitation. If you look at mitral regurgitation, you'll see the velocity is usually close to 5 meters per second. What we said, pulse wave Doppler can only measure 1.5 to 2 meters. So if you have mitral regurgitation, again, when you have mitral regurgitation, that MR velocity is usually of the order of 5 meters per second or more. So you can't use pulse wave Doppler. Okay, so we have an apical four chamber on top. Your cursor is right, yeah, sorry, your probe or transducer is right there. This is your left ventricle. The mitral valve is there. This is your left atrium. There is a flow. Okay, we put our, this cursor is there, sample volume is there. There's a flow below the baseline. And when we gate it, it's a systolic flow. So remember, systole is from the onset of the QRS to the T wave. Systole, onset of QRS to the T wave. So this is a systolic flow below the baseline. So what's happening, you get there's a flow from the left ventricle across the mitral valve into the left atrium. This is mitral regurgitation. Mitral regurgitation. Okay? The flow is away from the transducer or probe. Okay? And if you measure the velocity, so each of these is 2 meters per second. So this is close to 5 meters per second. You cannot use pulse wave Doppler for that. Okay? Similarly, with tricuspid regurgitation, you know, a lot of time the tricuspid regurgitation is going to be more than 2 meters per second. This one is 3 meters per second. Okay? So you can't use pulse wave Doppler. It has to be continuous wave Doppler. Okay? Continuous wave Doppler. So any eye flow, eye velocity flow, you have to use continuous wave Doppler. Similarly, if you're evaluating aortic stenosis and you put your sample volume into the aortic valve, you're going to get high velocities. This is different from measuring left ventricular flow tract velocity. If you're measuring the left ventricular flow tract velocity, you have to move away from the aortic valve. You have to be at least a centimeter or more away from the aortic valve. This is aortic stenosis, okay? And you put your sample volume right into the aortic valve, you're going to get a high velocity flow. You have to use continuous wave Doppler for that. If you look at your gate, you're going to see it's a systolic flow. Systole is from the onset of the QRS to the T wave. This is a systolic flow. And by measuring the velocity, we can convert the velocity into pressures or gradients. So that is continuous wave Doppler. Now, color flow Doppler. So you guys who have looked at echoes, you'll see all those colors that we have there, and you must wonder what the color means, or does the color mean anything? Yes, the color mean a lot. The color actually tells us the direction that the blood or tissue is moving in. Okay? The color tells us the direction that the blood or tissue, because we also have color, we can color code tissue, not only blood. This, you know, when we look at the heart contracting, we can color code that as well. But for right now, we just think in terms of blood. If the blood is moving, if the blood is moving towards the transducer, we color code that red. We color code it red. Blood moving towards the transducer, we color code that red. If the blood is moving away from the transducer, we color code that blue. Okay, so the different colors. And another very important point is that color flow Doppler is a form of pulse wave Doppler. Color flow Doppler is a form of pulse wave Dopplers. So the returning echoes is displayed as an assigned color. Flow towards the transducer or the probe are seen as shades of red, and flow away from the transducer are seen as shades of blue. When you have turbulence, you get a mosaic of colors. So it's a mixture of the colors. So any very high flow, disorganized flow, it's gonna look like a mixture. So it's not gonna be purely red or blue. it's going to be a mosaic, a mixture of those colors. If you have no flow, it's it's going to be black. No flow is black. The faster the velocities, is you get a brighter shades of the blue or red. So faster velocities are displayed in brighter shades of red or blue. So if you were to look, so again, you always need to look and see where your transducer is. Transducer is right here. Okay. So this red, that means the flow is moving towards the transducer. So if you remember your parasternal long axis view, blood is going to leave the left ventricle, across the left ventricular flow tract, across the aortic valve, into the aorta. So it's going to move somewhat towards the transducer. And that is why it is red. Okay? As opposed to this mitral regurgitation, transducers here, this flow is moving down. This is mitral regurgitation. That is why it's some shades of blue. Okay? Flow towards the transducer is going to be some shades of red. Flow away from the transducer, some shade of blue. Okay, your transducer is right there, short axis at the level of the aorta, the right ventricle, tricuspid valve, right atrium. This is a high turbulent flow. You see mosaic, it's a mixture color. So once you see that, you know it's a high flow. This is tricuspid regurgitation. So when you look at it, it's a mixture of the color, mosaic. Okay. Again, your probe or transducer is there. You get this blue color. So that means this flow is moving away from the transducer. This is aortic insufficiency. So this is your aortic valve. The blood is going backwards. It's moving away from the transducer. That's why it's blue. If it was moving towards the transducer, it will be red. So this is your aortic insufficiency. All right. So that is Doppler in a nutshell. You're gonna have to read extensively, build in that knowledge, and you need to know what flow is you know when you need to use pulse wave Doppler, when you need to use continuous wave Doppler, and we use color flow for almost everything. You need to color flow will give you a rough uh, direction of movement of the blood. Is it moving towards the transducer or is it moving away from the transducer? So you can first look at it with color flow Doppler, then you can move to your regular pulse wave Doppler, and then if you need to use continuous wave Doppler, you use continuous wave Doppler. Always remember that color flow Doppler is a form of pulse wave Doppler. All right, so